Okay, in this video, we study some basic properties of the multivariate Gaussian integral that are useful for calculating the mean and variance of the multivariate normal distribution. Okay, let's start. So, first of all, I assume that you already know the basic properties of univariate Gaussian integral. That is this. Integral from negative infinity to positive infinity of exponential of 1 over 2, let's say gamma, which is a positive constant, x squared dx. So I hope you already know how to calculate this integral, which results in 2 pi over gamma. Okay, and also by looking at this function, we see that this integrand is an even function. So if we calculate the first moment, like this one, so x times exponential of this, x squared, so you can immediately see that this should be equal to 0. And moreover, what about the second moment? So x squared times this exponential, gamma x squared dx. So I hope you can calculate this integral, and the result should be 2 pi over gamma square root times 1 over gamma. Okay? So this one you can obtain either by repeatedly applying integration by parts or differentiating this integral, both sides, with respect to gamma. So either way you can get this. Okay. So that's the preliminary results. We need to calculate some properties of multivariate version of this integral. So suppose we have a symmetric metric and positive definite matrix. Positive definite matrix. Let's say it's n by n. And x is a vector. So x1, x2, xn, n-dimensional vector. So the integral we are interested in is this. So we integrate over whole n-dimensional Euclidean space, this integral. Negative 1 over 2 x transpose gamma x dx. So this is n-dimensional multiple integral. And I have actually have another video how to show how to calculate this integral, but we do it anyway here. It's a repetition, but let's do it for the sake of completeness. So since we are assuming this gamma is symmetric and positive definite, we can apply eigenvalue decomposition. So this can be diagonalized by an orthogonal matrix V. And we have a diagonal matrix, let's say delta, and V transpose. Okay, so V is a orthogonal matrix, and delta is a diagonal matrix. Let's say delta 1, delta 2, and delta n. And all of these eigenvalues are positive. Now, if we apply this decomposition here, then we have this integral, exponential of negative 1 over 2 x transpose v delta v transpose x and dx. So now we consider these factors together. So we introduce this transformation, new coordinate, y equals to v transpose and x. Okay, so now this becomes y transpose and this becomes y. And also this, by this linear transformation, we have the Jacobian is actually 1. So Jacobian of this is this, but this v is orthogonal, so its determinant is 1. So it's just dx. So the transformation is very simple. Now let's do that, and we have 1 over 2 x transpose gamma x dx. So now we consider this factors together. So we introduce this transformation, new coordinate, y equals to v transpose and x. Okay, so now this becomes y transpose and this becomes y. And also this by this linear transformation, we have the Jacobian is actually 1. So Jacobian of this is this, but this v is orthogonal, so its determinant is 1. So the transformation is very simple. Now let's do that, and we have exponential of negative 1 over 2 y transpose delta y and dy. Now, let's consider this part. Since delta is diagonal, so y transpose delta is, if you calculate this, this becomes delta 1. So the delta 1 is the first eigenvalue, and y1 squared, and delta 2, y2 squared, and so on. So delta n, yn squared. So let's substitute this into this. Then we have exponential of a sum, which can be decomposed into the product of exponential. So this becomes product of exponentials. So exponential of 1 over 2 delta I yi squared dy. So let's expand this one. So it's an n-dimensional integral. So dy1, dy2, and so on, dyn. And each of these factors contain only one variable. So we can split this integral into the product of a single integral. That is this integral from negative infinity to positive infinity, exponential of 1 over 2 delta I yi squared dy. And now this is just a univariate Gaussian integral, which we already know the answer. So it's this. So it's square root of 2 pi over this constant. Okay, so in this case, it's not gamma, but it's delta I. So it's product of this and square root of 2 pi over delta I. Let's summarize this. And then let's see. So 2 pi is just a constant. So let's put everything here, 2 pi to the power of n. And then the product comes only in the denominator, delta I. So maybe we can write in this way, square root of 2 pi to the power of n and delta I inverse. Wait a minute, we have to take the product. Delta I inverse. So this is 1 over delta I, okay? Now, let's look at this part. What is this? This is the product of the inverse of eigenvalues, which is delta I inverse. So this is actually the determinant of the inverse matrix of this inverse of this delta matrix. Okay, so delta is a diagonal matrix like this, 0, 0, and its inverse, delta inverse, is like this, 1 over delta 1, 1 over delta 2, and so on, 1 over delta n. So this product, it actually represents the determinant of this inverse matrix of delta. Furthermore, the determinant is invariant under orthogonal transformation. So that means this determinant is actually equal to the determinant of gamma inverse. Okay, to see this, let's see. So gamma inverse is this, V delta inverse V transpose, because we have this eigenvalue decomposition here. And it's easy to check that if we define, if we have gamma inverse like this, this is indeed the inverse matrix of gamma. Okay, just try to calculate this, gamma and gamma inverse. So gamma is decomposed into this, and gamma inverse, if we have this, so let's try that. And this one, it's orthogonal matrix, so it's equal to identity matrix. So we have, and multiplying by the identity doesn't change anything, so we have this. So they are inverse of each other. So that's again identity matrix. So we have V and V transpose, which is identity, right? So this is indeed the inverse matrix of gamma. And to see that this is indeed equal to this, the product of determinant of a matrix product is the product of determinants, right? So if we want to calculate the determinant of gamma inverse, we decompose it. So V delta inverse, V transpose. So this is equal to the product of each determinant. Okay. But the determinant of this orthogonal matrix is 1. So it's just, so this is equal to 1, this is equal to 1. So it's just the determinant of delta inverse. So the determinants are invariant under orthogonal transformation of matrices. Anyway, so to summarize, the result of this Gaussian integral, exponential of negative 1 over 2 x transpose gamma x and dx is equal to this. So that is square root of 2 pi to the power of n times the determinant of gamma inverse. We are assuming this gamma is positive, positive definite, so of course the determinant is positive. Yeah, so this doesn't make any problem. Okay. Okay, next let's consider the first moment, by which I mean this integral. So x times this exponential Gaussian kernel, x transpose gamma x and dx. By symmetry, I think it's pretty much obvious that this should be equal to the 0 vector. By the way, this x is a vector, so the result should be also a vector. So this is a 0 vector. But let's show that more directly by using that transformation y equals to v transpose and x here. So we want to use this transformation, but we have x here. So how can we transform this x into this y? For that, this v is an orthogonal vector. So from here, we have vy. So we multiply both sides by v from the left. Then we have vy equals to x, because v times v transpose is the identity matrix. So we can use this. And so we have vy and exponential. And as we have done before, this exponent becomes y transpose and delta and y. And the Jacobian was 1, so we have this. Now, again, we split this exponential into the product of exponentials. So we can put v outside the integral because it's a constant matrix. And this product from I, let's say, okay, I to n, and exponential of negative 1 over 2 delta I yi squared dy I. Okay, so this y is a vector, and now we consider each element of this vector separately. Okay, so let's consider the jth element of this vector. So jth element becomes, so let's ignore this v for the moment, just write integral. This becomes yj and product of this dyi. So we need to consider two cases where this I runs from 1 to n. So one of these i's should be equal to this j. So let's consider that case separately. So we should have I from 1 to n, but except for j, we have just this exponential. Exponential of yi squared dy. So we have this on one hand times we have this times this exponential. So this yj times exponential of this delta j yj squared dyj. But we know that this is equal to 0. So this element should be 0, but j can be any element. So after all the elements of this integral becomes 0. And 0 times 0 vector, if multiplied by this matrix, it's still 0 vector. So as we have claimed before in the beginning, the result is the 0 vector. Okay, finally, let's calculate the second moment, by which I mean this quantity. X transpose times this exponential Gaussian kernel, X transpose gamma x dx. Again, we simplify this by using this transformation, V transpose times X, or equivalently, X is equal to Vy. So let's get rid of X using this. So this X becomes Vy, and X transpose becomes Y transpose. Wait a minute. Yeah, Y transpose and V transpose. And exponential of 1 over 2 Y transpose delta, the diagonal matrix Y, and again the Jacobian was 1, so it's just dy here. Now we can take these V and V transpose out of the integral, and we can split this into the product of exponentials, and we have this y transpose. By the way, this is a matrix, okay? Is that okay? Because y is a column vector, so y times y transpose is a matrix, and product. Let's use k as an index. Exponential and delta k yk squared dyk. Everything V transpose. Okay, since this is a matrix, it's hard to deal with. So let's consider the ij element of this matrix. So the ij element of this matrix, y transpose, its ij element is just yi times yj. So let's consider this integral. Yi, yj, and this product, k from 1 to n, delta k yk squared dyk. So when this k runs from 1 to n, two of them should match. So one of them should be I, and the other another of them should be j, right? Maybe I and j are the same. So let's consider two cases: when I is equal to j, or when I is not equal to j. First, consider when I is not equal to j. Okay, in that case, this integral, let's say it's I, so integral becomes this. So we just separate all these factors if k is not equal to I or j. So in that case, when k is not equal to I or j, we just take it out. So from negative infinity to positive infinity, exponential of delta k yk squared dyk. So this is okay. Times this integral. So we have double integral. Actually, this is just yi and yj. We can separate these two. So let's write like yi exponential of delta I yi squared dy times and yj exponential delta j yj squared dyj. But we know that this integral and this integral, they are both 0, right? Because it's due to the symmetry. Okay, so when I is not equal to j, I mean, in other words, if for the off-diagonal parts of this matrix, off-diagonal elements are all 0. Okay, so next case, when I is equal to j. In that case, we can separate similarly to this case, but instead of these two factors, we have only one factor that contains yi squared. So the integral becomes the product, so not equal to I. And so j is equal to I in this case, so we can just put I here. So anyway, so that's exponential 1 over 2 delta k yk squared and times integral, we need this, and yi squared and this delta I yi squared dy. And from this part we get just the first Gaussian integral, that is k not equal to I square root of 2 pi over delta k. Okay, from this part we get square root of 2 pi over delta I times 1 over delta I. Again, this is from the property of the univariate Gaussian integral. Okay, so let's, we have this thing and this thing, the very similar thing together. So let's combine them, and we have, okay, so we have 2 pi to the power of n and delta I inverse. Wait a minute, we have this product here, not I, let's say k from 1 to n delta k inverse, and times 1 over, let's say, delta I inverse. Okay. And as we have seen before, this part is equal to the determinant of gamma inverse. So let's write it like that, 2 pi to the power of n, determinant of gamma inverse, times delta I inverse. So to summarize, this matrix, this one, becomes a diagonal matrix of whose diagonal elements are 1 over delta I. So let's see. So V and integral y transpose and exponential of this dy and times V transpose becomes this. So V and this. By the way, so okay, this is a diagonal. So this matrix is actually the inverse matrix of delta, right? And times this constant. Let's say times this constant. 2 pi n and inverse determinant. What is this? This is actually, let's put this constant first. 2 pi n gamma inverse. This is equal to gamma inverse. So that's it. So that's the final result of the second moment. So in the multivariate normal distribution, we have something like this: exponential of 1 over 2 x transpose sigma inverse x, like this. And of course, there is a normalization factor, 2 pi to the power of n, and the determinant of sigma. Here, sigma is the covariance matrix, right? So if we integrate, if we calculate the expectation value of x transpose using this density function, the result should be, since we divide by this, the result should be just sigma. So it's inverse of this. So inverse of inverse is the original matrix, which is the covariance matrix. So that's how we get the covariance matrix from the multivariate Gaussian distribution or normal distribution. For the mean of the multivariate normal distribution, we calculate, let's consider more general version of the distribution. So in that case, the mean is this mu here. This is the mean. And the covariance inverse and x minus mean. So given this distribution, let's see, we calculate this integral. So this density times vector x dx. So to do this calculation, let's say we define a new variable, z equals to x minus mu. So then this becomes z, and this becomes z, and this x becomes z plus mu, right? So if we distribute this, so there is z times this density. So if we integrate this, that's 0, as we have shown. And now the remaining term is mu times this, and mu is a constant. And so we just integrate this function as it is, and times this constant mu. So the result will be just mu, because it's normalized here. And that's how we get the mean and the covariance of the multivariate normal distribution. Okay, so that's it for this video. See you later.